electron which is visible for the positive side. So this is the only difference that we see.
Okay.
Okay. So moving on to the next part where we discuss the dark trions in two-dimensional materials. So now similar to, we discussed about bright and dark excitons earlier. Let me go into a little bit of details of what I mean by that. So in tungsten-based compounds and also in molybdenum-based compounds, the conduction bands are split a few tens of MeV due to spin orbit splitting. Now, transition is allowed in two-dimensional materials only if the spin of the valence band, a spin of a hole in the valence band, is same as a spin in the conduction band. So now it turns out that in tungsten-based material, the lowest conduction band has an opposite spin than the top of the valence band. Therefore, the lowest energy exciton is dark in energy. So this does not dark in nature. So it does not interact with the photon. However, in molybdenum-based materials, it has been said that the lowest energy. Now, these might have pronounced effects on the optical emission properties of the materials. For example, if the lowest energy state is dark, then it would, it would freeze most of the carriers in the lowest state, and these carriers would not be able to emit. So therefore, the material will not be an efficient emitter. So we must investigate these materials, which of these are dark and which are bright. Now, Thorsten, again, our colleague who does GWBSC calculations, he finds that there should be two types of bright trions depending on where the electrons and holes are in the band structure, and there should be one dark trion. So this is the case for tungsten disulfide and tungsten diselenide. In fact, the dark trion in tungsten disulfide or selenide, it should be lowest in energy. It should be the lowest energy transition. So then this would mean that the dark trions would be very important to the emission properties, because now they are the lowest transitions and they are dark. So they will take most of the carriers and freeze them in this state, and they will not be able to emit. So they will be inefficient light emitters. In fact, now, since dark trions do not interact with light, so it's very difficult to probe them optically. There are only two reports so far, which we know, and they are on tungsten diselenide monolayers, where it's found that this material has lowest energy trion, which is dark. Also, there are controversies about MOS2. For example, if MOS2 is bright or dark, it's not settled yet. This report told that MOS2 should be actually a darkish material, which is contradictory to this picture, with this theoretical picture. It showed that the dark state should actually be many tens of MeV below the bright states. So this inspired us to make this study, make this investigation. In fact, this work took us a long time. It took us rather 5 years of time before we reached an appropriate conclusion, after making many repetitions and after producing high quality samples and so on. But finally, we are able to give an answer on this. So now I want to first introduce you to the concept that the trions follow a Fermi-Dirac distribution of electrons. By that, what I mean is, if you have a population of electrons in a doped semiconductor, we have drawn conduction bands here in the K plus and K minus valley, then in the absence of any magnetic field, when these levels are degenerate, the two populations should be of the same order. However, when you apply magnetic field, you can shift one of the populations in the second valley. These are only this. Now we are talking about electrons here. Now, since for the creation of trions, you need extra electrons, therefore you should not be able to create any trion in this valley, and the trions should be only created in this valley. So the oscillator strength of trions should be highly quenched in one of the valleys than the other in the presence of magnetic field. So if we think that the trions also follow the Fermi-Dirac distribution of electrons, then we should be able to tell that as a function of magnetic field, the trions should be, the oscillator strength of trions should be proportional to this, the Fermi-Dirac distribution, where delta ECB is a conduction band splitting with magnetic field. Now, for seeing this effect, we apply high magnetic fields to study the absorption of trions. To create high magnetic fields, the generation is done in a laboratory in Grenoble, high magnetic field lab in Grenoble, where we have a resistive magnet, which is done by 24 megawatt power supply, which can be thought of to be equivalent to 3 or 4 bullet train engines, trying to pump this magnet together or trying to charge this magnet together. It needs 64,000 amperes at 400 volt to charge this magnet, and a huge pump is required to cool this magnet. There are other processes to create high magnetic fields. For example, there can be single coil experiments where a single coil of copper can be taken and a high amount of energy, such as a few megajoule, are passed in this single coil within a few milliseconds. And the coil blows up actually, but one can create very large magnetic fields. For example, I can show you a video from Japan High Magnetic Field Lab. I hope you will be able to hear the sound. Okay, so the experiment actually blows up, but since there is an explosion, the sample survives and one can still measure on the sample again. In fact, the record of high magnetic field generation is with Russia, where they created 2800 Tesla of magnetic field with a simple single coil. But what they did was they put explosives outside the coil, and when a lot of energy from a capacitor bank was discharged in the coil started to blow up. But at the same time, the explosions outside the explosive outside the coil were also blown up, and this led to an implosion of the coil, and so therefore the magnetic field actually rose to 2800 Tesla. However, since this is a recorded session, unfortunately, I am not allowed to show that video because of confidentiality reasons. Okay, let's come back to high magnetic fields, to trions. So this is the spectrum of trion in MOSE2. This is a reflectance spectrum. We measured this back in 2015, but took some time to understand things and publish later on. So these are two circular polarizations, and one can see that they are similar in intensity at 0 Tesla, because the two cases, the two valleys are degenerate. However, when you raise the magnetic field, you lead to separation, the Zeeman splitting between the two bands. And then what you find is that one of the valleys, which is this red valley, where most of the electrons are coming, the trions gain the oscillator strength, whereas in the other valley, the trions lose oscillator strength. So one can actually fit this polarization degree here by Fermi-Dirac functions, and one can find the G factors of the conduction bands and so on. The message is that the trions follow a distribution of electrons, a Fermi-Dirac distribution of electrons. So following this concept, let's study photoluminescence with temperature. What we assume is that there is a dark state in tungsten disulfide, and then there are two bright states above, a few MeV above, or a few tens of MeV above this dark state. At low temperature, most of the carriers, we assume, then would be frozen to this dark state, and the emission from the material will be low, because only these states emit, so the emission will be low in intensity. But when you raise the temperature, then some of the carriers will go there due to Fermi-Dirac distribution, and then the emission should increase in intensity. Okay, so one can write actually the photoluminescence as a multiplication of number density in the bright state multiplied by the oscillator strengths in the bright state. So one has to consider both things, the oscillator strength and the number density. So number density is written again by Fermi-Dirac distribution, where x minus x minus d is the energy separation between bright and dark state. And this is the oscillator strength. So let's look at the photoluminescence spectrum, where top one is the 5K spectrum. Let's only look at the trions. We do not consider the other peaks at the moment. So what we see is that when you raise the temperature, the trion intensity seems to rise, and then it falls. And in fact, when we plot the trion intensities, what we find is that there is an initial fall, then there is a rise, and then there is a fall. So these are the integrated intensities of these trions. Now, we understood that the trions should give more light when you raise the temperature. However, there is a fall in the intensity which is not understood. In fact, there is an initial fall which is not understood. The answer lies in this second factor, which is oscillator strength, which we directly measure from absorption. I already showed this data to you. So the two trions, their absorption reduces with temperature by a scheme which I already discussed. And then one can fit these oscillator strengths as a function of temperature by a phenomenological function, as Fermi-Dirac-like function. And now we have known these oscillator strengths. We also know a separation between two bright trions from experiment. So we have this unknown parameter which can be obtained after fitting the spectra. So we find that the spectra actually fit very well with our model with only this unknown parameter. And we find that the separation between bright and dark trions is 19 MeV in this material. So the dark trion is actually 19 MeV below the bright trion. In fact, if we compare with another report from literature, which is a direct measurement of this dark trion, then we find that this is 20 MeV there, and it compares very well with our value. In fact, the initial reduction is also captured in our model, which is a very simple model. So then, having confidence that our model works well, we go for other materials. We find that for tungsten diselenide, absorption and luminescence behave similar, and we find that the dark trion lies 19 MeV below the bright trion. So this is a dark material. For MOSE2, we find that the dark trion lies above the bright trion. So this should be a bright material. In fact, it's only 6 MeV above the bright trion. Whereas for MOS2, which is a mystery, we find that both dark and bright trions are rather degenerate in energy. They are very close to each other in energy. So it's a mixed state. So finally, we say that the Fermi distribution of combined population of dark and bright excitons, it governs the PL and absorption in two-dimensional materials. And we find that MOS2 possesses a mixed bright-dark character. So to summarize the whole talk, I discussed about scattering states and the bound excited states of the trions initially, and we find that they exist in the solids. And then we say that using a simple Pauli blocking picture, we can explain the absorption processes as a function of temperature. We find that the emission can be explained by a Fermi-Dirac distribution, and we find that tungsten-based materials are dark, MOSE2 is bright, whereas MOS2 is a mixed bright-dark state, bright-dark material. I would like to thank my collaborators, the experimentalist group in Muenster, where the 3 students have worked really hard for producing high-quality samples on which we worked on. Theory group of Professor Michel Rolfing and Dr. Thorsten Dielmann has always been very supportive to us in explaining all the results that we obtain either in high field lab or in Muenster. And also Marek Potemski and Piotr Kosatsky have been very close collaborators in this work. Thank you very much. I am open for questions.
Okay, thank you, Ashish, for a very nice talk. And now the session is open for questions.
Hello?
Yes.
Okay, so am I audible?
Yes.
So I have 2 questions regarding. So firstly, can you please once again explain? You're saying something about the spins and the dark trions actually. For the first slide where you actually explain trans. Can you repeat that point? I can't really get the thing, what you're actually saying about the spins.
Yes, actually, I did not go into details of that slide for sure. So we can discuss that now. So for creating any bright trion, what we need is, first we have to see where the bright exciton is. For example, in tungsten-based compounds, this is K minus valley. So you have a downspin here and a downspin here that creates an exciton. And then now you can put another electron either in this band or in this band or in this band. Yeah. So this makes a bright exciton trion, and then when you make the other electron here, then this makes the other bright trion. In fact, you can, or you are also allowed to put this electron in this higher band here, meaning here. But in that case, it's found that this trion is not so bound. The binding energy is really, really low, so we are not expecting to see it. Therefore, we only see these two bright trions. However, for producing a dark trion, for creating a dark trion, you need opposite spin electrons in the same valley. So that will be creating a dark exciton, and then you can put another electron either here or here or here. So similar to the other cases, it's found that if the electron is there or there, the trion is not very effective to the spectra because it's higher in energy. However, this trion is the dark trion, which is contributing the most to the optical processes.
So to have a dark trion, actually we need to put the electrons in opposite spin. That is the most needed point, and it should be on the same value, right?
That's correct.
I mean, okay. And another thing I want to ask is about the last slide, I guess, the slide before the summary one.
Okay.
So can you just? Okay.
Yes.
So
I hope I am close. Yes. Here.
yeah. So in the so this is the slide. So here we can see that for the material WAC2,
yes,
the dark trion state actually lies beneath the light trionic state, and
yes,
for MOAC2 actually is above, and
that's correct.
MOS2 is between
Yes.
between the two lights. So
Yes.
is there any determining parameter where it should lie, or any prediction depending on the material type or the sample type, how it's actually
Yes.
or is just an experimental evidence that it lies there, but is there any strong way to tell that this going to be this or that? I mean,
Yes. So the thing is, I mean, in the lowest order, one can try to look at the conduction bands, the conduction band splittings, the ordering of conduction band splittings, for example, using DFT and performing a GW correction to say how the conduction bands are aligned. Is a dark state is favored or a bright state. However, when you add excitonic and trionic effects to that, then you have to do a full-fledged calculation, which Thorsten does, and then it's not so easy to predict without without solving Bethe-Salpeter equation. It's not very intuitive to know which should be bright and which should be dark. This is what I understand.
okay, thank you.
You're welcome.
Hello.
Yeah.
Yeah, actually, I have a few questions. So,
yes.
First question is that when we talk about the scattering states for the trions and the excitons,
yes.
So usually we say that the exciton and trans energy states lie below the conduction band and in the band gap of
yes.
the. So then from where because scattering state means you are saying that scattering with the electrons, right?
Yes.
So since the electronic states are in either the valence band or in the conduction band,
yes.
but the states for the exciton and trans are in the gap. So
yes.
how the scattering is possible there?
Actually, I think we are talking of two different pictures now. One is the single particle picture, which is similar to what I have shown here, where if you put, where you are allowed to calculate the band structure only when you put a single particle, for example, an electron and a hole, then you get such kind of bands. However, when you, as soon as you introduce Coulomb interaction, you are not rather allowed to talk in this picture, and then you have to go to the band structure of the exciton. And in that case, then we cannot directly say that the exciton lies between electron and hole bands. In fact, it's a completely different entity. It's a completely different phase space. So we cannot club these two phase spaces together. So the answer is not that related to the single particle picture which we are talking about.
Okay, so
can I rephrase the question? I think the question is actually quite interesting.
Yes.
Yeah. So what I said that the energy state for the exciton and strands are lying in the band gap of the semiconductor,
Yes.
as said that in the, because considering the single particle picture. But when we talk about the scattering states, so scattering means scattering with the electrons.
Yes.
But the electronic state are either in the valence band or in the conduction band.
Yeah. So that's
So-
what. So I think yeah.
Okay.
So because say for instance, if you look at an exciton,
Yes.
right? So the exciton 1s level and 2s level and 3s level and so on
Yes.
should all merge to the conduction band edge,
Yes.
right? So you can't have any at least if you look at excitons, you can't have any excitonic state which is above the
Yes.
band.
That's correct.
So
But still, yes.
I think the question is that what is it that is different about the trions which you don't see, right? Because trions are also essentially bound states.
Yes.
So you would expect that all the bound states n equal to infinity
Yes.
will actually merge with the conduction band with the
With the
edge,
exciton.
right? At energy zero energy, right? So
No, they will not.
merge.
No, they will not merge with the conduction band. They will merge with the exciton.
In
Yes.
zero energy, right?
Yes.
So why is
correct.
it that the 2s states are so much above the
No, so the 2s states
edge?
which, yes, so the 2s states which you just talked about, indeed they lie below the exciton level. However, they are singly charged 2s states, meaning only one of the electrons is in the second state or in the third state, that will be 3s state, but the other electron is inside here. In that case, let's see if I can draw something here with a pen. So let's suppose I have a hole here. Then if I have 1s level here, and if I have an electron here, somewhere there, then I have an option to put the next electron there, or so on, or in the next orbit. So these states would be below the exciton state. For example, if let's suppose this is my exciton and this is my trion. Yeah. Okay, my drawing is not so great in this, but then there could be these states here of the trions, which we just talked about. This will be the, for example, 2s state, this one. However, the state which we are talking about now, which is this one, so this state is actually above the 1s exciton. So there is this 2s exciton now. And so this exciton is like you have a positive charge here, and then the negative charge lies on the second level here, and then you are allowed to put an electron in the same level or in the next levels. So those will be the states which will be somewhere there just below the exciton. So if this is the exciton, this is the 1s of trion, then this. So essentially this is the excited, so this is the ground trion states of the excited exciton, if one wants to say it. So it's not that easy to imagine, I understand, but is it confusing
I
or
also
clear?
have to think about it, because even
Yes.
the 2s exciton state is below the gap, right?
Yes.
And okay, so I have to think about it. Okay.
Yeah, of course, the band gap is somewhere there. So the 2s exciton is there, 2s trion is there, and so on. In fact, I can also call this a 2s trion, but this 2s trion belongs to 1s exciton. So it's below the 1s exciton.
Can I ask one more question?
Yes, please.
So I have one basic confusion that when we talk about that the K state for any particle, just like for the electron in this semiconductors, we know that since the K state are available because of the Bloch momentum, crystal
Yes.
momentum.
Yes.
But when we talk about the two-dimensional exciton or trans, we know that
Yes.
these are the bound state in the two-dimensional space.
Yes.
So confined in the z direction.
Yes.
And how the means momentum degree of freedom is coming in this picture? Is it similar to the electronic state like that?
Yes. Actually, in the XY plane, you still have a movement of electron that's allowed. So in XY plane, you can draw a parabola still.
Okay,
Yes.
that is clear. But in the XY plane, I'm talking about the momentum for the exciton or trans, because these are the bound state in the XY plane itself, right?
They are bound in the Z plane, but in the XY plane, they are still free to move until their diffusion length is reached. If that answers.
Okay, okay. So
even exciton and trion are free to move in the XY plane.
Okay. Okay, and just last question
Yes,
related to the magnetic field measurement.
please.
So just like when we talk about that, when we place a normal electron in a magnetic, there is a formation of Landau level. Is
Yes,
it possible for that in the presence of high magnetic field? This because these are the charged particles, they
correct.
can interact with this magnetic field. They can form itself some sort of the Landau level for the
Yes.
excitons and trions.
Yes. So the thing is the following. We have to consider energy scales here. So energy scale of magnetic field, for example, 10 Tesla magnetic field is of the order of 1 MeV energy scale. Yeah. So now the binding energy of excitons in these materials are of the order of 300 or 400 MeVs. So you will need very, very high magnetic fields so that you start to see any Landau level formation because the exciton is so strongly bound. The binding energy of the exciton dominates till really, really large magnetic fields before magnetic fields start to actually split the exciton in the form of, when they start to move the excited
Yeah.
states, we say it like that. Yes,
Okay. Thank you.
you're welcome.
Ashish,
Yes,
can I ask?
please.
This diagram that you just sketched is very reminiscent of the Rydberg series in a two electron atom.
The right one? I'm sorry, Shiva, I'm not able to hear you very properly, but let's try still.
These levels between the doubly excited state of the trion and the others that you were talking about,
Yes.
they are very reminiscent of the Rydberg series in, for example, a typical helium-like atom,
Remnant
right?
of Rydberg-like series of? I missed
Of
that.
of of a two electron atom.
Two electron atom. Yes, that's correct. H negative.
At the doubly excited state, typically in atoms you see a Fano-like profile for the line shape.
Correct.
Is I mean, is it possible to sort of
Yes.
have a double of that in trions as well?
Yes. So in fact, we also expected a Fano-like effect in our 2s state because it's lying on the continuum of these scattering states of the oneness trions. So you are very correct. However, we do not see a strong interaction of this 2s state within our experimental accuracy with the background of excited or the scattering states of trions here. So we do not see any variation in the line shape, unfortunately. We had expected that, but we do not see it.
Ashish, I have a question.
Yes.
So, do these trions always exist in a material, or they keep on forming and kind of disappearing?
So you can create them optically, number one. Also, at certain temperature, you are always creating some population of excitons. Yeah, you have some holes and some electrons which are always forming. So you are always creating some trions and they keep on disappearing. That's correct.
And does it also depend on the interaction between electrons and holes in the system?
Definitely. So the oscillator strength strongly depends on the effective masses, number one, which dictates how strongly the exciton or trion would be bound. So the exciton binding energy would be like dependent on this strength, and this will also decide the oscillator strength of these resonances, these species.
I see. So can we say that, for example, lighter electrons and holes do not, systems with lighter effective masses do not have many of these, or it's not?
This statement would be in general correct. However, there could be other things. For example, if the dielectric screening is reduced a lot, the dielectric because in the explanation of these bound states, you have epsilon at the bottom in the denominator. So if you reduce that, you can still increase the binding energy.
I see. Thank you.
You're welcome.
Hi, Ashish.
Yes.
Yeah, I have a rather stupid question.
No question is stupid.
No, I'm not from this field, right? That's why. My question is regarding these trions. So,
Yes.
so when you're modeling trions, you're assuming basically H minus, right?
Yes.
But you could also do it as He plus. So why are you taking into consideration that your positive quasi-particles is at rest, for example?
Yes. So when we, so this is a very good question. So when we measure the nature of doping in our system, we find that our systems are negatively doped. Therefore, we consider the system where there are extra electrons than extra holes. So it would be a similar system rather for positively charged trions, the one which you suggested. However, one has to take care about the effective masses, because in H negative systems or He positive system, the protons are like 2000 times heavier than that of the electrons. So that model will just fail when we come to a solid, because here the electrons and holes are of similar masses. So one has to do a full-fledged calculation of the individual particles to know what would be bound and what would be not.
Okay. And I have one more question. Sorry.
Yes. Yes.
Regarding this interlayer exciton, when you said about it is the candidate for Bose-Einstein condensate.
Yes.
So what is the criteria you expect to get a Bose-Einstein condensate in this system, for example?
So essentially, this is a candidate because these are specially separated excitons. Now, an exciton is a boson altogether. And when the wave functions of electrons and holes are strongly overlapping with each other, their lifetimes are very small. However, when you separate the wave functions in the neighboring layers, then you expect that their lifetimes are large. And in fact, when you create dark interlayer excitons, which is rather another different species, then they will be really long-lived. And one expects that they will be sufficiently long-lived that one can observe possibly Bose-Einstein condensation of these species.
Thanks.
You're welcome.
Hi Ashish, I have a small question. That first one is like, this is very analogous to the atomic physics we are studying. So there is like a high electric field, like Stark effect thing.
Yes.
There.
So Stark effect normally for these bound excitons, it has not rather been seen because of very strong binding energies of these excitons. However, for interlayer excitons, it has recently been seen. In fact, there are 3 papers on arXiv at the moment, which tell that when you apply electric field, you are able to shift the interlayer exciton resonances. In fact, you are able to create 2 interlayer exciton resonances out of 1, where electron and hole are either in the upper layer or electron or hole are in the lower layer, and so on. Yes.
One more thing, I am just little curious, that's why I'm asking.
Yes.
So like, is it there any probability like quadrupole like kind of a thing, like a 2 exciton are bound together?
Yes. So these states are also seen. So these are called bi-excitons, and these states appear somewhere between the trion and the neutral exciton. So somewhere between. However, you have to pump very hard to start seeing any luminescence from these states. So because the intensity of emission from these states increases quadratically with laser power. But I think their oscillator strength in absorption is still very small, because not many of such species are available to absorb in low excitation intensities.
Thank you, Ashish.
You're welcome.
Hi, Ashish. Avik here. My
Avik.
question is that you have this also this another species, right? Like these zero phonon lines which have been predicted and I guess in some cases observed also, right? So
in which material?
In WSC2, in MOS2 on HBN, I guess these zero phonon lines. Did you guys ever see these?
Would you call the zero phonon line as the normal exciton line or something else?
Just above that, when you have this, this direct transition with zero momentum transfer, a very, very sharp line with, 2, 3, 4 centimeter inverse width kind of thing.
Okay, so far we have not seen an evidence of that, unfortunately.
Okay, so nothing of that.
Have you seen it?
Okay. Yes, and some others also have seen it. So I just wanted to know if, but they come only, of course, much below 10 Kelvin. around 4
Okay.
Kelvin. So I was wondering if you guys have done any detailed studies on those.
In our spectra, we have not seen so far.
Okay, thanks. Yeah, okay.
Yeah.
Hi, Ashish. I have one
Yes.
question. When you show us the 1s and 2s state temperature dependence spectra,
Yes.
I see that in the 2s state, the trions and the excitons, the intensity difference is very much similar. Intensities are just similar for the 2s, but it is not in the case of 1s.
Is this correct? Let's go back to
Why is so?
Let's go back to the intensities for the 2s states. I think it's here. So yeah, so this is the picture which we are talking about, right?
Yeah.
Okay, so what's the question again? Sorry.
So the intensity difference between, for example, X1s, T1s, and X2s, T2s.
At low temperature, you mean their oscillator strength is similar?
Yeah.
Oh, this is a difficult question to answer because this would require some calculations which converge the oscillator strengths of excited states very well, and I am not aware of such calculations which exist so far within the computational requirements that will be there for such oscillator strengths, because the oscillator strengths are really hard to converge in the calculations of trions. So it will be very difficult to say why the oscillator strengths are similar in the case of excited states and very different in the case of ground states.
Thank you.
You're welcome.
I had a question actually, naive question probably.
Yes.
So recently there has been systems where you can obtain flat bands. So flat bands actually increases the effective mass.
Yes.
So in such a system, do you expect that these trionic states to occur more in probability with higher absorption strength or something?
One should think about it for sure. I think you are talking about Moire superlattices, where at certain angle about 1 degree or so, or 1 to 2 degree,
1.05 or something,
something like that. Right. So you are able to create flat bands. I'm not sure if there are any theoretical studies or experimental studies so far on Moire superlattices about trions, because theoretically, of course, it's really, really challenging, which I hear from my colleagues. It's very, very tough to do even DFT on Moire superlattices, and then we have to include Coulomb interaction and to solve Bethe-Salpeter equation. I think this is not possible so far. So I am not sure how to answer this question. I apologize.
Okay. Another question probably, is it possible for these states to exist in indirect bandgap systems?
You mean indirect, you mean momentum indirect trions?
Yeah.
Oh, sure. I think such states should exist. Momentum indirect trions should exist. However, they will be optically dark because just that the band gap is indirect. So it will be very tough to detect them. I think nothing prevents them to create such indirect trions, because in a trion, the momentum can be conserved anyway by the use of this third electron. The third electron can share the momentum part. So in principle, it's possible, but in reality, it might be difficult to detect them. You're welcome.
Okay, are there any other question?
I'm just tempted to ask, so
Yes.
can you put a number on the absorption coefficient in centimeter inverse?
Of the order of between 10 raised to power 5 to 10 raised to power 6 for exciton, because it absorbs really strongly for encapsulated samples.
Okay.
Yeah.
Thanks.
All right. If there are no more questions, we. Oh, yeah. Go ahead, Jaggi.
Thank you. Ashish, since you have the slide up right now, may I ask
Yes.
you a question from an outsider? I'm not in the field.
Sure.
Thing that you have circled here, the integrated absorption as a function of temperature
Yes.
for the T2S and X2S.
Yes.
When you were describing it, my eyes lit up because your explanation made complete sense to me.
Okay.
It seems really reasonable that because the creation of the trions needs 2 electrons, its probability depends upon the availability of
Yes.
2 electrons in the valley, and at higher temperature that gets less likely. So that
Yes.
was a very coherent explanation from the point of view of an experimentalist. But then it prompted the question,
Yes.
as the temperature is increasing, in some sense, the T2S is getting empty, right?
Yes.
Fewer of those.
Yes.
Would that lead to some kind of interesting effects on the line widths of the X2S as a function of temperature? Like they're so close, and they are they not coupled in terms of some strange kind of line width behavior?
So I am really happy that you asked this question. I had avoided to tell this detail earlier. So in fact, what we find is, which we probably can, let me find my pointer, which we probably can also see by eye, that the exciton starts to become narrower when we raise the temperature. So as soon as the trion is...
Much better than mine. That's what I was staring at, and I couldn't tell. But please go on. Thank you.
let me zoom in.
Yeah, thank you. Yeah.
So the exciton starts to become actually narrower when we are raising the temperature. And this is a very interesting effect. And in fact, this falls exactly in the explanation which we were trying to give in this paper, that initially there is a state to which the exciton can relax to, or exciton can be converted to a trion. Therefore, its line width is large. Now this state disappears and this relaxation channel is gone. And then the line width becomes small because its lifetime becomes large. So this is, in fact, in this paper, we have actually plotted this line width versus temperature, and it's a very interesting effect for sure.
Thank you. Now, once you zoom in, I can see clearly that they are in fact sharpening as a function of temperature. And
yes.
This is like internal evidence that your explanation is sound. It has internal consistency.
Yes, because in principle, when we raise temperature, normally we always expect the line width to increase. But this is counterintuitive, but this fits exactly in the explanation. Thanks for pointing this out.
Well, thank you for explaining it. Thank you.
So, Ashish, I can't resist telling you this, that there is a very interesting situation where you can have features that get sharper
yes.
with increasing temperature.
Yes.
And one such example is in a superconductor, insulator superconductor tunnel junction.
Okay.
Where you have, if you take 2 superconductors, then you have 2 peaks in the conduction spectrum,
okay.
conductance spectrum, one at delta 1 minus delta 2 and one at delta 1 plus delta 2.
Okay.
Now the one at delta 1 minus delta 2 with increase in temperature gets sharper exactly for the same reason.
I see.
Because you have one channel that gets blocked.
Okay.
But it should be a coherent channel, right? Because if it's an incoherent channel, then it won't happen.
Yeah.
So if there's a coherent channel, there should be some tunneling and some splitting also, which should change, or?
Yeah. So now, effectively, what happens is that as you increase temperature, you have some excited carriers, and that keeps blocking one of the channels. So that causes this other feature to get sharper.
Okay.
Interesting.